Here's one more question posted on College Board for students to prepare for the AP exam questions. It's one of their FRQs. And the question states, students have a battery of EMF, EMF, with neglectable internal resistance and many identical resistive heating elements, and will connect a circuit so that the heating elements can be used to heat some water. Each of the heating elements has resistance R. First, the students consider connecting the heating elements in series with a battery as shown on our right on the top. One student says that to heat the water faster, they should use as many heating elements as possible. Write an equation for the power P dissipated by a current containing n heating elements in series in terms of E, R, and N. N is the number of elements. And physical constants as appropriate. Does the equation support or refute the student's claim about the time it takes to heat the water? Justify your answer. So if there are n elements in a circuit, then we know how to calculate the power. The power formula states that the power is equal to I times V, or I squared R, or V squared over R. If I use Ohm's law, V is equal to IR, and replace my I or V in the formula, I will get the last two formulas. So the power is equal to that, and your current, well, actually, I can use the last part because the EMF is given, so I know the voltage and the resistance of each one of them. But the total resistance in the circuit with n of the elements, so here you have 3, but they tell you there are going to be n elements, heating elements. So one student says the more elements you connect, the better it's going to be, the faster the water is going to be heated. So you can prove that the power is equal to EMF squared divided by, and if you have n elements, so your total resistance is going to be n times R, because each element has resistance R, divided by n times R. So the first part, they say write an equation for the power dissipated by a current containing n heating elements connected in series in terms of the variables that they gave you. So that would be the answer for A, or the first part. And for the second part, they say, does the equation support the refute of the student's claim about the time it takes to heat up the water? So the student says that the water is going to be heated faster with many elements. What we see from this equation is that the power drops the more n elements, the power drops the more elements you have. So it looks like the student is wrong, because the more elements you add, the less power is going to be produced. The less heat is going to be given to heat up the water. Pause for B, try to solve B yourself from what you understand from A, and always try to solve questions at first on your own before you watch the videos or look for the answers, because you will understand better if you do try to solve questions yourself. So for this question, another student suggests that connecting a heating elements in parallel might be a better idea. The student says that a certain number of elements in parallel will heat the water faster than the same number of elements in series, because the current in the parallel circuit will be less. Write an equation for the power P dissipated by the circuit containing n hidden elements in parallel in terms of the EMF R and N, which is number of the elements, and physical constants is appropriate. Does the equation support or refute the student's claim about the time it takes to hit the water? Justify your answer. And is the student's claim about the current correct? Justify your answer. So when you have elements in parallel, and I'm going to show you an example on 3 of them, but they say there's n of them. I'm going to use 3 for now. I have 1 over r plus 1 over r plus 1 over r. And I always tell my students when we have resistors in parallel, they could use that the 1 over the summative resistance is equal to 1 over R1, 1 over R2, and so on. They could use this formula, but instead of using this formula every single time, we have like little saying that we use all the time. So you could say 1 over, the result flip over. So I have 1 over first one, 1 over the second, 1 over the third, but they're all the same. So it looks like I'm going to have 3 over R. So my total resistance of 3 resistors connected in parallel, I have R over 3. And if I had 4 of them, I would have over 4. And if I had 5, I would have over 5. So if I have n elements, my total resistance becomes R over n. Then the current that is leaving the battery, because in the last part they asked about the current. So the current that leaving in the battery would be EMF divided by R over N, or in other words, it's N times the EMF times R. So the student says that the current in parallel circuit will be less. So that means this claim is wrong. The current actually increases in parallel connection. If you had a series connection, like in the previous problem, your total resistance with n elements would be NR. So your current would be EMF divided by R times N. So here in series connection, your current is low. But when you connect them in parallel, your current goes higher and higher with every single resistor you connect. Because if this is I, and this is I, and this is I, then in order for this to be I, this to be I, this to be I, this would have to be 3I. And with n elements, it would be n times I. So that claim is wrong. And then for the first part, they say write an equation for the power dissipated by. So I can write the equation again. I know what my total resistance is equal to. So the power is equal to V squared over R, and it's R over N, R over N. Let's write it this way. It's gonna be V squared divided by the total resistance, which is R over N. So the power is equal to N times the EMF squared over R. So it looks like the more number of components or hidden elements you have in your circuit, the more power you produce. And the more power you produce, the more energy you heat, because the power is how much you work. So it's work per second. So that's how much heat per second you're giving away to heat up the water. So that would be the formula. This would be the formula that you would use for the first part. And for the second part, does the equation support or refute the student's claim about the time it takes to heat up the water? And again, this is how much energy given per time second. So you give more energy per second. So that this formula does support that the student claimed suggestion that connecting heating elements in parallel might be a better idea to heat up the water.